Hello, Calculus. These are the video notes on Extrema. So we have 3 definitions or vocab words that we're going to be referencing throughout this lesson. We have absolute extrema, local extrema, and critical points. And so the first example we're going to be talking about are the absolute extremum, which are your absolute maximums and your absolute minimums. Now you can see that an absolute maximum occurs if the function at the given value c is greater than or equal to all other function values in the domain. Vice versa, you're going to have a minimum if the function value at that location is less than or equal to all other function values in the interval. So the examples from the textbook, pretty clear. Just going to talk you through each one. So our first example is your cubic function on an infinite domain. It has neither a maximum nor a minimum. We'll see later that this point in the middle here, where the derivative is actually 0, is just going to be called a critical point. Example 2 has an absolute max of 1, and it has no absolute minimum because these are extending towards 0, approaching 0, as the function approaches infinity on either side. Cosine, on the other hand, has an infinite number of maximums and an infinite number of absolute minimums. Over here, this is where students tend to get in trouble. The absolute maximum is located at x equals 0, and the absolute max is 2. So endpoints can be maximums and minimums, absolute max and absolute min, but this does not have an absolute minimum. The lowest point here is an open circle, and so it's not actually in the domain. Over here, we have an absolute maximum of 4 at 4 and an absolute minimum of 0 at 2. And then over here, we have an absolute minimum, but because the function approaches infinity, we do not have an absolute maximum. For local extremum, and I'm going to add notes, you want to be able to classify each point on the picture as it applies. So right here, this peak stands out. This is an absolute maximum. Absolute extrema that do not occur on the endpoints can also be classified as local extrema. And this is very similar to the way that a square can also be classified as a rectangle, since it has all of the features of a rectangle as well. Down here, you have, let me switch colors, a local minimum. We do not have an absolute minimum in this photo. You can't quite tell because it's been cut off, but this does go towards infinity. So when in doubt, a function that's being cut off, you have to assume it's going towards infinity unless it specifies otherwise. And then finally, right here, we have a local max. So a single function can have multiple extrema points of different varieties. What makes a point critical? So up in the definition at the beginning of the notes, the definition of a critical point is any point where the derivative of the function is either 0 or undefined. Now having a extrema, local extrema, does guarantee that you have a critical point, but having a critical point does not guarantee that you have either a maximum or a minimum. So you can see for the first 3 examples, these are each maximums or minimums at the critical points. But by the time you get to the next 2 examples, we have a critical point, but we don't have an absolute extrema. So this is a one-way statement. Having a local extrema implies a critical point, but having a critical point does not guarantee you have a local extrema. Let's take a look at some examples. So the first examples we want to do are via a graph. Either the graph will be provided for you, or you will use a graphing calculator to complete the graph. So I've got this TI-84 Plus emulator TI is offering this for free for 90 days due to all the shutdowns. And so I'm going to use this to get a graph going of my first function. So we've got 1/3 x to the third power minus 5/2 x squared plus 4x. And as you can see, this emulator just updates the graph automatically for me. Ooh, oh, over here on this third panel. And so I'm going to draw a sketch of this on my notes. Let's see if I can keep both of them up at the same time. No, I cannot. Okay, memorize it. We've got kind of this going on, and this going on, and that going on. And then we just want to identify each of the features that we see. And so the table can help me identify these. It does appear that we have a local maximum, a local minimum, but we do not have any absolute maximums or minimums because the cubic function extends to both positive and negative infinity. So let's identify that maximum. It looks like the maximum is occurring at about 1-ish. So if I look at my table, let's change our table settings and let's just go for a decimal counting. Oh, you know what we can do is we can calculate. So we're going to hit second calculate, and we're going to calculate a maximum, which is the fourth option. Usually something happens. Oh, there we go. Just a little delay. So the first question is going to say left bound down here at the bottom. Just make sure your indicator is to the left of the maximum and hit enter. Then it's going to say right bound, so you are going to have to use the arrow pad to scroll over, hit enter, and then guess, hit enter again. And we can see we have a maximum at about 1,1.833. And so my guess is that's an actual fraction value. That's quite nice, but we're not going to worry about that. Local max, 1,1.83. Then do the same thing for minimum. So go to second calc and select minimum from your window by pressing 3. Get to the left of your minimum, hit enter, get to the right of your minimum, and hit enter, and then when it says guess, hit enter one last time. So we have our local minimum at 4, negative 2.67. And that's how we're going to identify minimums and maximums graphically. Let's try that again with the next example. If you want to, pause the video here, try the example, and then play to see if your answers match up. Okay, my graph is fully updated, and I can see that this graph does not have any maximums. It does have an absolute minimum. Absolute minimum. And it's got a couple critical values, that aren't actually local extremum. So that looks like it's at exactly -1 and +1. We kind of have this inflection point here, the minimum, and up. So let's calculate this absolute minimum. It does look like it's at exactly 0, -1, and if you look over here at your table, you can see it is 0, -1. What do we call these points right here? So what are we referring to with our x-intercepts? So -1, 0, 1, 0. Both are inflection points. These are called critical values, but they do not qualify as extremum. All right, let's take a look at the last example. Again, I would recommend you pause the video, get a graph going, try to predict what the solution is going to be before I reveal that solution to you. So we've got 4x in the numerator, 1 plus x squared in the denominator, and we're going to go ahead and graph. So with this function, I actually see both an absolute maximum and an absolute minimum rather than a local. And from the table, it almost appears that they're occurring at positive 1. Can I scroll up on my table? No, okay. It does appear that they're occurring at positive and negative 1. So I'm going to switch the table start to negative 2. Is that going to fix it down here? Okay, so here's my table view. That way I can see, yeah, so we've got an absolute minimum at negative 2 of negative 8/5, and our absolute max is positive 8/5 over at positive 2. So absolute max 2, 8/5. If you give this as a decimal, that's absolutely fine. Absolute min was negative 2, negative, well, that's negative 8/5. And the function kind of sort of looked like this. Passes through 0, 0? Yeah, it does. No, that's not right. Erase that, start over, up, and then asymptote. Perfect. Okay, so we're looking at our max,